Today we face a matrix where every diagonal must hold the same number. Can you decide if this grid follows that rule? Pause and think. What would you check first? Let's start from the very beginning. The input is a two-dimensional array, often called a matrix, with a certain number of rows and columns. Each cell contains an integer. The task is to return true if the matrix is a Toeplitz matrix, otherwise false. A Toeplitz matrix has a very specific property. Every diagonal that runs from the top left toward the bottom right must contain exactly the same value all the way down. In other words, if you pick any cell and move one step down and one step right repeatedly, you should always see the same number. For example, consider a 3 by 4 grid. The first row is 1, 2, 3, 4. The second row is 5, 1, 2, 3. The third row is 9, 5, 1, 2. Look at the diagonal that starts at the top left corner. 1, then 1, then 1, all equal. The diagonal starting at the first row second column gives 2, 2, 2, also equal. Every such diagonal in this example stays constant, so the answer is true. Why is this not trivial? Because a matrix can be large and there are many diagonals to verify. You might be tempted to collect each diagonal into a list and check for duplicates, but that would use extra memory and extra passes. The constraints tell us the matrix dimensions can be up to several hundred rows and columns, so an algorithm that does a constant amount of work per cell is ideal. We need to output a simple Boolean, true if every diagonal is constant, false the moment we find a mismatch. The obvious thing to try is to examine every cell and compare it with the cell that sits one row down and one column to the right. You would loop over all rows and all columns, and for each position that still has a neighbor down right, you check whether the two values match. If any pair differs, you can immediately say the matrix is not Toeplitz. This approach visits each cell once and does a constant time comparison, so the total work is proportional to the number of cells. That's O, m times n time. The memory usage stays big O of 1, constant time, because we only keep a few counters and a Boolean flag. However, the naive double loop as written in many first attempts includes an extra bounds check inside the inner loop for every single cell, even for cells on the last row or last column where there is no down right neighbor. That means we waste a tiny amount of time checking conditions that will never lead to a comparison. It's not a big asymptotic problem, but it shows we're doing a little redundant work. We're iterating over the entire grid even though the last row and last column never participate in a diagonal comparison. The brute force idea is correct and already optimal in big O terms, but we can tighten the loops to avoid those useless iterations and make the code cleaner. The key insight is simple. You only need to compare each cell with its down right neighbor, and you only need to do that for cells that actually have such a neighbor. That means you can stop the outer loop one row early and the inner loop one column early. In plain English, iterate over every row except the last, and inside that iterate over every column except the last. For each of those positions, check if the current value equals the value one row down and one column right. If any check fails, return false immediately. If the loops finish without a mismatch, return true. Let's walk through the code line by line in words. First, we read the number of rows, call it row count, and the number of columns, call it col count. Then we start a loop with a variable row index that goes from 0 up to row count minus 2, that stops before the last row. Inside, we start another loop with col index that goes from 0 up to col count minus 2, stopping before the last column. At this point, the current cell is matrix row index col index, and its down right neighbor is matrix row index plus 1 col index plus 1. We compare those two numbers. If they differ, we instantly know the matrix breaks the Toeplitz rule, so we return false. If they are equal, we continue to the next column. When the inner loop finishes, we move to the next row. After all rows and columns have been processed without finding a mismatch, we return true. This version does exactly the same number of comparisons as the brute force idea, but avoids the extra bounds checks and makes the intention crystal clear. We only look at cells that start a diagonal segment. Now let's trace the optimal algorithm on the example matrix with 3 rows and 4 columns. We have row count equals 3, col count equals 4. The outer loop runs for row index equals 0 and row index equals 1, since row count minus 2 equals 1. The inner loop runs for col index equals 0, 1, 2, since col count minus 2 equals 2. We will list every iteration with all variable values. First outer iteration, row index equals 0. Inner iteration 1, col index equals 0. Current cell matrix 0, 0 equals 1. Down right neighbor matrix 1, 1 equals 1. Compare 1 and 1, they match, continue. Inner iteration 2, col index equals 1. Current cell matrix 0, 1 equals 2. Down right neighbor matrix 1, 2 equals 2. Compare 2 and 2, match, continue. Inner iteration 3, col index equals 2. Current cell matrix 0, 2 equals 3. Down right neighbor matrix 1, 3 equals 3. Compare 3 and 3, match, continue. Inner loop ends for row index equals 0. Second outer iteration, row index equals 1. Inner iteration 1, col index equals 0. Current cell matrix 1, 0 equals 5. Down right neighbor matrix 2, 1 equals 5. Compare 5 and 5, match, continue. Inner iteration 2, col index equals 1. Current cell matrix 1, 1 equals 1. Down right neighbor matrix 2, 2 equals 1. Compare 1 and 1, match, continue. Inner iteration 3, col index equals 2. Current cell matrix 1, 2 equals 2. Down right neighbor matrix 2, 3 equals 2. Compare 2 and 2, match, continue. Inner loop ends for row index equals 1. Outer loop ends because row index would become 2, which is not less than row count minus 1, 2. No mismatches were found, so the algorithm returns true. Every variable value at each step has been spoken. Row index, col count, row count, col index, the two matrix values and the comparison result. The algorithm returns true for the example because every diagonal element matches its down pair was equal, confirming the matrix is Toeplitz. You'll spot this pattern when a problem asks you to verify that all diagonals in a grid share the same value, or when you need to check a constant difference property across rows and columns. Look for phrases like each diagonal is constant, or matrix ij equals matrix I plus 1j plus 1. Time complexity is O, m times n, because we examine each relevant cell once. Space complexity is big O of 1, constant time since we only use a few integer counters. Try the next diagonal matrix problem, same pattern. Subscribe for more beginner-friendly DSA walkthroughs.